All right, so we're switching kind of our focus to just springs, and oscillations, and then also we'll bring pendulums back in. Both springs and pendulums behave according to the rules of simple harmonic motion, at least in an ideal case. Simple harmonic motion is also used to explain lots of other phenomena that don't involve springs and pendulums, such as the motion of atoms in can be described as simple harmonic oscillators. The motion of electrons are described as oscillators. When you start getting into quantum mechanics, a lot of our thermodynamics and the way that particles behave in terms of kinetic molecular theory, a lot of those are actually modeled using simple harmonic motion. So we're going to take a look at what it means to be in simple harmonic motion, some examples, and how do you describe mathematically objects moving in simple harmonic motion. So the first thing we have to realize that when we are looking at oscillating systems, so we're going to focus on springs here primarily, then the transition to pendulums. The first thing is that the acceleration of the block when it's oscillating a spring is not constant. So your spring force is going to be your net force. Your net force is mass times acceleration. Your spring force is k delta x. So what this means is it means your acceleration is dependent on your displacement. So when we want to use the kinematic equations, any of the kinematic equations all assumed that acceleration was constant. So this is not the case when you have an object oscillating on a spring or an object that is on the end of a string that's acting as a pendulum. When you have a bigger displacement, you are going to end up with a larger acceleration. When your displacement is zero, you have zero acceleration. So we cannot use the kinematic equations, but we still want to be able to describe the position, velocity, and acceleration of these particles as functions of time. So we need to find a different way to do that. Well, in your lab, you had a mass oscillating on the end of the spring. What you find is it's actually a sinusoidal function. And so we describe the motion of objects on a spring kind of like we would a wave or a circle. A lot of the vocabulary is going to be the same. The same thing is going to be true for a pendulum, except for instead of oscillating in terms of a linear displacement, you're oscillating in terms of an angular displacement. So just some different terms to recognize. The amplitude is essentially the displacement from equilibrium. So you need to have an equilibrium line, which is in here somewhere. There it is, your equilibrium line. So whenever you hang the mass on the spring, we usually set that to essentially be displacement equals zero. And then your amplitude would be the displacement from that, either up or down. There is a maximum amplitude that is represented with the variable a usually, and that is the maximum displacement that is possible. But realize that it's only the height of a crest or the height of a trough. It's not a total height, okay, because it's measured from the equilibrium position. The period is the time for one complete oscillation. So this wave goes through one complete oscillation starting here, coming up to a crest, down to a trough, and returning to the center line. Now, it's easiest to measure that from, say, a crest to a crest or from a trough to a trough, rather than looking at the midpoint. Because if you look at the midpoint, the wave is actually going to go through the midpoint an extra time. So you don't want to go from middle point to middle point. You need to go from two equal points in the oscillation. We use a cosine function to describe the position. Now, if you go and look up online at different resources, sometimes you'll see it as a sine function. And either works, because remember that the cosine function, the sine function are identical in frequency, period. They could be identical in amplitude. They're just phase shifted in time. So basically that you're going to get a cosine function that is going to start at your maximum amplitude, whereas a sine function is going to start at an amplitude of 0, at a displacement of 0. So depending on resources you look at for help, sometimes you'll see it as a cosine function or a sine function. Now, this is not the version of the equation that is on the AP Physics 1 formula sheet. I believe the version that's on the AP Physics 1 formula sheet actually uses the frequency, which we'll talk about in a minute, but they're going to use x is a cosine of 2 pi f times t. So they're going to use that version instead, and they're going to use the frequency here. But there's a relationship between the frequency f and the angular frequency. But this is a much simpler way to write it. This is the way that I usually write the function myself, is I prefer just to use the angular frequency. So the angular frequency is in radians per second. It relates a lot to the way circular motion behaves. Your capital A is your amplitude, usually in meters. Your time will be measured in seconds, and your displacement is any position x, not specifically the amplitude. So any function, any motion that could be described by this cosine function is going to be simple harmonic motion. So the pendulum that we look at, the spring oscillating, those are all going to be examples of simple harmonic motion. And simple harmonic motion is periodic, so it repeats itself in time. And then it's oscillatory, which means it takes place over a limited spatial range. So it goes back and forth between these same positions. But there is a lot of oscillating motion and periodic motion that is not simple harmonic, because simple harmonic motion must be additionally described by this cosine function. So this, for example, is a graph that shows the displacement in terms of omega t. So basically it's the inside, essentially, of that cosine function. So you can see that you're going to have some sort of zero line, and then it's going to oscillate on either side. And if you have a nice perfect cosine function, you're going to be at your maximum amplitude, essentially when t equals 0. But the problem is, this probably happened to the people that were doing a physical lab, is that when you start, say, your motion detector, it doesn't necessarily catch t equals 0 at the maximum amplitude. So sometimes you'll have your 0 line be somewhere in between this perfect looking cosine function, or maybe it's even offset so much that you're actually getting more of a sine function rather than a cosine function. And that's because inside of that cosine, there's also a phase shift, which shifts this function left and right. But you're going to get this kind of general motion out of it. So the amplitude is the maximum displacement in either direction. And the one thing that is really, really important to realize about the amplitude is the amplitude of the oscillation does not affect the period or the frequency. So here is a wave that has a particular amplitude. So we've got that amplitude here. Here is a different oscillation that has a larger amplitude. And these both have the same period, because we go from crest to crest in the same amount of time. And so if you change the amplitude of the displacement, so for example, if I have a mass here on the bottom of a spring, and this is its resting place, this is where we set displacement equals to 0. Gravity and the spring force are balanced right here. So if I were to displace it, say, to this position right here, and let it go and oscillate, or if I were to displace it to this position here and let it go and oscillate, and as long as I'm staying within the feasible range of the behavior of the spring, then this is going to oscillate back and forth in the exact same period. So the difference is that because this one has a bigger stretch, it's going to have a bigger speed essentially when it reaches the middle point. So it'll be able to kind of go faster through a bigger distance, whereas the blue one goes slower through a smaller distance, and both are going to end up with the same period. Now, this idea of this angular frequency is related to the angular velocity, essentially, of a circle. So circular motion, uniform circular motion, is going to be also simple harmonic motion. So, for example, if you take this vector A and that vector can essentially move through a circular path, then if we wanted to describe the x component, that x component here can be described based on a cosine function, where essentially the angle theta is going to be omega times t, where omega is your angular velocity. And so you can see that the x component of this would be the amplitude a, which is basically the radius of this circle, times cosine of omega t. And that would be the x component. The y component could be described in simple harmonic motion with a sine function. So y would be a sine of omega t. So that's why we can use either a cosine or a sine function, because both are going to oscillate periodically. Now, basically, if we use kind of that circular representation, we can represent the relationship between omega and the frequency f. So the frequency is basically the number of cycles per second. So the number of cycles per second is called a hertz. So that's a capital H and a lowercase z. We use hertz for frequencies for like sound and things like that, but it's for any oscillation, so not specifically simple harmonic motion. And then your frequency is omega over 2 pi. And so that we talked about this a bit, so I can do a cosine of 2 pi f times t, or I can do a cosine of omega times t, because those are equivalent. Now, your omega is going to have units of radians per second. Your hertz there, so basically when you take radians per second and you divide it by 2 pi radians, the radians cancels out, so you just get a per second for that unit. Now, the period is 1 over frequency, and your frequency is 1 over period. So you can actually relate all of those together. And the AP formula sheet has a relationship written between period, frequency, and omega. So that's not something you have to memorize. It's on your formula sheet. So looking at this, we have a position function. So this is x as a function of t. And so if you notice that we're starting out the cosines, so we're starting at our maximum amplitude A, and then you go to 0, and then at half of the period, you will be at your negative amplitude, and then you come back to the middle, and then once your full period, you are back to that maximum amplitude again. And this is described by a cosine function. Now, we know that velocity is essentially change in position over change in time, or if you're doing calculus, it's the derivative. So if I were to look at the slope of the position time graph right here, then that slope is 0. So my velocity needs to be 0. If I look here at the middle, that's going to give me my steepest slope, so my largest velocity, and it's negative, so it's going to give me a negative value. So that when that's 0, my position displacement 0, my velocity is actually at a negative maximum. And then I have a slope of 0 again. So we're at 0. And then we come through here, we're going to be at a positive maximum for the slope. So that's going to be our velocity at that point. Then we're going to go to 0, and then to a negative maximum, and then to 0 again, and so forth. Now, this is not a cosine function. It's actually a sine function. And because it goes negative first, it's a negative sine function. So you can always find the relationship. You can figure out what the velocity graph is going to look like from the position graph. Now, also remember that acceleration is the change in velocity over change in time. So it's the slope of a velocity time graph. So if I were to then look at this velocity graph, I'm going to have my steepest slope right here at the start, and it's going to be negative. So my acceleration actually has to be negative maximum at that point. Then the slope of that velocity graph is going to be 0 right there. So I'm going to get 0 for my acceleration. Now notice my displacement and my acceleration are 0 at the same time. And then when I come here, that's a positive maximum. So I'm going to get positive maximum slope. So I'm going to have positive maximum for my acceleration. And then I'm going to be at 0 again. And then I'm going to be at a negative maximum. And I'm going to be at 0. And it's going to keep on going and having that pattern. So your acceleration function is also a cosine function, but it's actually a negative cosine function. And it's really important to understand that when your displacement is either at a positive or negative max or min, then your velocity is 0 and your acceleration is going to be at a max or min, but it's going to be the opposite direction. So if your displacement was positive, your acceleration would be negative. When your displacement is 0, your acceleration is also 0, and your velocity is at a maximum. You'd have to figure out whether it's moving in the positive or negative direction to figure out if that velocity is positive or negative. And then your displacement and your acceleration must always have opposite signs. Now, you can also look at these functions and recognize that the amplitudes of these graphs are going to be a little different. So the maximum values for each of these are going to be slightly different. I think I have this on the next slide. There they are. So that your x max, your maximum displacement, is going to have a magnitude of a. Your maximum velocity is going to have a magnitude of a omega. And your maximum acceleration is going to have a magnitude of a omega squared. Now, like I said, if you know calculus, then really all you have to do is memorize the first one, because then you just take subsequent derivatives with the chain rule to get the other ones. Now, if you don't know calculus, memorize the equations. That's probably the easiest thing to do. The AP exam only gives you the first one. And once again, I think they give it to you in terms of 2 pi f. So these are just some reminders of things that I just talked about. So your omega is in radians per second. That's your angular frequency. That is not really angular velocity unless you're talking about a circle. The displacement, velocity, and acceleration are all defined by sine or cosine functions. Your maximum velocity is going to have magnitude of a omega. Acceleration is going to be a omega squared. The acceleration is going to have maximums at the same locations as the displacement, but in the opposite direction. And your velocity is going to have a maximum magnitude when your displacement and acceleration are 0. Now, basically, every mass spring system has what we call a natural frequency. And this is the natural frequency in terms of omega here, or it's the same thing as 2 pi f, and that's going to be the square root of k over m. So basically what this tells you, if you have a larger k, which is a stiffer spring, then you're going to get a larger angular frequency. So it's going to oscillate faster. If you have a bigger mass, you're going to have a smaller angular frequency. So your bigger mass is going to oscillate more slowly. Now notice that there's no amplitude anywhere in this. So change in the amplitude does not change the frequency of the oscillation. Now on the AP formula sheet, they give things in terms of periods. They give you that the period of the spring is 2 pi times the square root of m over k. So period and frequency behave the opposite. So if your mass is larger, your period is larger. If your spring constant is larger, your period is smaller. So these are there for you, so you don't have to have it memorized. And the problem I see is some people, when they try and memorize it, they flip m and k, and then they get the opposite. So you don't want to do that. So the same thing can be true of a pendulum. So let's actually go back here for a moment and go back to these equations. So when we're looking here at these equations, this is in terms of a linear position. But I could do this same thing for an angular position, but I would use theta of t. And this is going to be a cosine of omega t. And then it's really weird to do this because your velocity time is going to be an angular speed, but angular speed and angular frequency are different. So I'm just going to define the change in theta over the change in time is going to be negative a omega sine of omega t. And then your acceleration would be alpha is a function of time. And that's going to be negative a omega squared cosine of omega t. So in this case, omega for angular speed, which is change in theta over change in time, this does not equal omega here. Okay, so those are not the same omegas. So it's really weird to do that. So I usually write out delta theta over delta t if I'm talking about angular speed, or I'll write out angular speed. And I'll write out the words angular speed is equal to negative a omega sine of omega t, just to make sure you're not getting confused. You won't have to use this very often in physics 1. You'll see it more often in physics C. But if we are looking at a pendulum, then there is also a natural frequency for a simple pendulum. A simple pendulum is defined as a point mass at the end of a string of length L. And you can see that the period of the pendulum, which would be t of the pendulum, is going to be 2 pi square root of L over G. And once again, this is on your AP Physics 1 formula sheet. So the longer the string, the bigger the period. So if you have a long string, it's going to take longer to go back and forth. If you've ever been to the Houston Museum of Natural Science, they have that huge Foucault pendulum. It has the circle with the little triangles all around. And the idea is it goes back and forth, and it knocks one down every 15 minutes. That is a really, 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 really long string. And so it takes a really long time for it to go back and forth enough time to be able to knock down the next triangle. Now its period isn't 15 minutes because it oscillates back and forth more often, but it is a very slow period. Now, it also depends on the acceleration due to gravity. So if you're in a bigger gravitational field, it's going to oscillate at a faster rate. So you're going to have a smaller period. So if you were to take a pendulum to the moon, which has 1/6 the gravitational force, it's going to go square root of 6 times slower. So you can end up relating period for your pendulum and your spring. And once again, this is independent of amplitude. So if I bring it back to a larger angle theta, theta 1. If I bring it back to a different angle of theta, that doesn't change the period of the pendulum. Now, generally, when we talk about pendulums, we need to keep our theta approximately less than about 15 degrees. We call that a small angle because otherwise things start going wonky and it doesn't behave like a perfect pendulum. So we usually have our pendulums operate on a small angle. Now, there's also a physical pendulum. So you could picture like some old like grandfather clock with some like pendulum oscillating or holding a ruler by one end and swinging it back and forth. Any type of pendulum like that's called a physical pendulum, and it's dependent on its moment of inertia and the length and the acceleration and mass. So it's dependent on a lot more things. This one is not on your AP formula sheet, but I've seen physical pendulums on the AP exam, but it's more conceptual. So it's understanding the fact that if you were to have a bigger moment of inertia, that you would have a smaller angular frequency because it would resist changes in rotation more. That would kind of be kind of the relative point there from that. And if you actually treat a simple pendulum as a physical pendulum, you can actually relate them together. And basically what you find is that a simple pendulum is just a special case of a physical pendulum. So if you let the moment of inertia of the physical pendulum be ml squared, then you end up getting the square root of g over L from this. So your simple pendulum is just a special case of a physical pendulum. Now, we talk about simple harmonic motion in terms of forces, in terms of what we call a restoring force. The restoring force is the force or net force that is responsible for the oscillations. So the restoring force is very, very particular. So in particular, the magnitude of the restoring force is always proportional to displacement. So if you look at a spring system, our spring system, the restoring force is the spring force. And so if you increase the displacement, you're going to increase the spring force. So those are proportional. So the spring force is going to be a restoring force. Plus, the restoring force must always be in the opposite direction. Remember that when we write the vector form of this, that if the spring force is to the right, it's because your displacement has been to the left. And so your restoring force always acts in the opposite direction of the displacement. The restoring force, as a result, is always directed towards the equilibrium position. So if I were to have like a spring here and a block, if this was my resting length, x equals 0, then when I stretch it this way, my spring force has to be pointing to the left because it has to be pointing towards the equilibrium position. When I compress it over here, the spring force acts to the right, which also points towards the equilibrium position. And then the restoring force is always equal to 0 when at equilibrium. So looking at a mass spring system, I think it's pretty obvious to see that if you have a horizontal system, your spring force is going to perfectly obey this relationship, because we just kind of talked about that. So that as you look at the equilibrium position, which is right here, that when you're to the right of the equilibrium position, it's being stretched. You're going to have a spring force to the left, and it's going to be bigger the further away you get. And then when you move over to the left, your spring force acts to the right, and it gets bigger the further away you get. Now, in a vertical system, well, but there's gravity. What else is going on? There's got to be gravity. Is gravity part of the restoring force? Well, no. The gravity is not actually part of the restoring force, because gravity always points down. So it only sometimes points in the direction of equilibrium. It's not always in the opposite direction of displacement. So gravity isn't. But doesn't it seem like we should have to consider the gravitational force? Well, yes and no. It's there, but it's not actually part of the restoring force. And here's why. Because when we stretch the spring by putting a mass on it, it already stretches. So that basically when it's hanging here, it's in equilibrium, so that the gravitational force and the spring force are equal to each other. And that's where we essentially set delta x is equal to 0. That's our equilibrium line. So realize that we can actually take a look at some of these relationships and prove that the gravitational force is not part of the restoring force. So if we look at some position, in this case the equilibrium position, our gravitational force and our spring force are going to be equal. So we can actually write an expression that tells us that mg is equal to k delta L, where delta L is this original stretch. Okay, so this is the original stretch here, delta L. So remember that. So now if we look at any other position, so in this case, our net force is going to be our gravitational force minus our spring force. In this case, we're defining the downward direction as positive just based on this position right here. So when we've lifted it up and we let it go, so we're lifting it above the equilibrium position to give it a displacement. So there is a restoring force. That you have a net force, and that net force is your restoring force, because it's acting towards the equilibrium position. If I were to have pulled it down, then the net force would be acting up. So the net force is our restoring force. Now, that net force is going to be the gravitational force minus the spring force. So the spring force is going to be based on the fact that we've actually now changed the amount of stretch. So now the amount of stretch is delta L minus y. Okay. So that's the actual displacement. So it was originally stretched at some delta L. We're now lifting it above that stretch point, so that now our position is delta L minus y. Now, if we distribute that, we get k delta L and then ky. But we had learned from the previous slide that mg was equal to k delta L. So when you sub in mg for k, or you sub in k delta L for mg, you sub that in right here, you get k delta L minus k delta L minus ky. Well, those two k delta L's cancel. We find that our net force is just negative ky, which is going to be the spring force when we've lifted it up a displacement of y. So our net force is just the spring force. So yes, there's a gravitational force. Yes, it's affecting our system, but it is not governing the oscillation. It's governing the position of the equilibrium line. So whenever you're working with a vertical system and you're talking about the restoring force or the spring force, it is the same thing as the net force. Just said that. Now, for a pendulum, this one's a little different. So when we talk about the restoring force for a pendulum, we're going to pull this thing back to some angle theta. So you're going to have some sort of angular displacement. Now, you have two forces. You have the tension and you have the gravitational force. Well, your tension here is parallel to the string, which means it has no component that is parallel to the displacement. So the tension is not acting as a restoring force. The gravitational force is. Now, if you resolve it into a triangle so that your gravitational force has an x component and a y component, the y component here is going to cancel out, or the component that's parallel to the tension is going to cancel out. And that's why the string doesn't get longer or shorter. It doesn't get stretched. But the x component of this triangle is still left. And so your restoring force is gravity, but it's not all of gravity. It is just the mg sine theta portion of gravity. I said that. Okay, just said that. So the restoring force for a pendulum is mg sine theta. So that if you have a larger theta, you are going to have a larger horizontal, a larger tangential component to the circle. So mg sine theta is going to get larger if you have a larger theta, and it also acts in the opposite direction as the displacement. So if I displace it left, it works to the right. So therefore, the mg sine theta meets the requirements for a restoring force. So that gives you some of the basics of simple harmonic motion, talking about position, velocity, and acceleration as functions of time, and also this idea of the restoring force in horizontal springs, vertical springs, and pendulums. We also talked about the period of a spring, a pendulum, also a physical pendulum. Our next topic is going to be over energy during these oscillations, but this gives you kind of a good starting point for being able to draw graphs of simple harmonic motion and analyze some of the dynamics and kinematics.